I'd like to introduce Dr. Podest. She's at NASA JPL, and she is actually one of our C's mentors. So if there's anything that you have questions about, she has a little bit of time in the next couple of weeks that she'll hold office hours and would answer questions for you about your projects. I'm going to turn it over to you because I know that the kids will have lots of questions from you, Erika.
Great. Thank you very much, Cassie. And thanks everyone for being here. I'm super excited. I've supported the CEAS program for a couple of years, and it's always like super interesting for me to see the sorts of projects that you guys engage with and how you bring your creativity to address like super important science questions. So what I wanted to bring today is the satellite perspective, right? So I understand that you're doing projects related to like the impacts of climate change on land cover. So I wanted to give you an introduction into the type of data that we collect about our planet from all of these numerous satellites that are orbiting around our Earth. So before that, just wanted to give you a little bit of background about myself. I am originally from Panama in Central America. I was born and raised there. And I was very much exposed to the outdoors from a very young age. And that developed, or I developed like this just love for nature and just deep curiosity about nature. So my family, my parents were super outdoors. Every weekend we were out in either exploring new areas, we were hiking, camping. And so those are my parents and my brother. And so we would often go to a Gatun Lake. So that's the Panama Canal. There's a lake in the middle, and my parents, they had this little, what we call an island. So it was basically a ranch, and we would go there every weekend and go fishing or swimming, or there are all sorts of really cool activities in this little John boat. And one of the things that my father would love to do with this little boat was to go up little streams and rivers. So if you've ever been to Disneyland or to Disney World, there's a boat ride that goes like through a jungle. So I would do that like every weekend, except like the real thing. And he would turn off the engine and we would just sit there for 30 minutes or so and just hear everything around us. And pick out what sort of animal that was or what sort of bird it was. Sometimes we would even see animals coming down to the river to drink, or it was really an amazing upbringing that I had. But I always thought I wanted to have a career related to science, related to better understanding our environment and helping preserve it. That's really what has driven me. And here I am in that boat again with my brother. We're out fishing, and sometimes we would camp out. That's the ranch that you saw, and we would do like really cool things, like we would go catching caimans, and my father would actually catch them, the small ones that he could grab with his hands, and then we would take pictures, and then we would release it. Yeah, so it was just kind of a little adventure that we would have, and that's me in the middle. That's me again, walking around that area in the Panama Canal, huge tropical trees. And then one of the things I did as well was I was in a race, ocean to ocean cayuco race. So cayucos are these long boats made out of one piece of wood, and they would fit normally 4 people. And so we would start in the Atlantic and end in the Pacific over a 3-day over 3 days. So the race was divided into 3 days where we would cover the entire Panama Canal. So as I thought, okay, well, I want to do something that's engaging, that has to do with our environment, I thought, okay, well, engineering would probably be a cool thing to study. So I studied electrical engineering because I thought technology would solve all of our problems, and I wanted to be part of that. So I studied engineering, electrical engineering in the United States. And as I was, and through my studies, I thought, well, maybe the next step for me, the master's, I can really focus that in using technology toward better understanding our planet, or development of technology toward better understanding our planet. And that's where I discovered this amazing field called remote sensing, which is the observation of Earth through satellites. And I did my master's in the UK. And as part of my master's program, I had to do a thesis, a master's thesis. And I got an internship at JPL to do my thesis research. And so that was the first opportunity for me. And sometimes, you know, those opportunities, those internship opportunities are so amazingly valuable because that opened up other opportunities, right? So I did my master's, and then after my master thesis was done, my mentors at NASA at JPL, which is where I am here, this is one of the many NASA centers, told me if I was going to pursue a PhD, to also consider doing my PhD thesis with the same group at JPL. So again, one opportunity led to another. I did my PhD, and then I did what's called a postdoc, and then I was hired on as a scientist. And this was over 10 years ago now. So I just wanted to show you this image showing different NASA centers. So each NASA center is focused on something very specific. I'm at the Jet Propulsion Laboratory, and JPL, also known as JPL, is focused on the unmanned exploration of our universe, right? So it includes obviously planet Earth, and we have just satellites to do this exploration. So we have satellites that are observing our Earth, and we send satellites to other planets, or we send rovers, for example. So that's JPL, sorry, that's in LA, in Los Angeles, in the Pasadena area. And, you know, JPL has sent satellites to every planet in our solar system. And it has also sent rovers to Mars. So those famous rovers that you've heard about on the news, Perseverance, Curiosity, Spirit, Opportunity, they have all come out of JPL. It's all unmanned, right? And recently there's not only a rover, but there's a small helicopter on Mars. So anyway, I'm very lucky to be here. I love the place I'm working. There are a lot of exciting things, but I am focused on planet Earth, remote sensing, using satellite data to observe our planet. And NASA has a number of Earth observing sensors in space. I'm not going to call them satellites. I'm going to call them sensors, because some of these sensors are on satellites. Some satellites have multiple sensors. And there are actually sensors on the International Space Station. So there is a fleet of these, I think on the order of 24, it changes. And these, what you're seeing here are the different satellites that are in orbit, or sensors that are on orbit around our planet. And these are just the NASA ones. International cooperation is extremely important for us. So there are other satellites and sensors in space, which data we use. And these are from the Japanese Space Agency, the European Space Agency, the French Space Agency, German Space Agency, Italian Space Agency. I'm actually working on a satellite mission. We'll launch the satellite next year. And this is in collaboration with the Indian Space Agency, and that satellite is called NISAR. So data is extremely important, and sharing data obviously is extremely important. It's not just about the US, it's what other countries do that impact US, or what the US does that impacts other parts of the world. And these satellites, they really, they're focused sensors. So some sensors make observations over the ocean, other sensors make observations over land, other sensors make observations about our atmosphere. But together, they provide this big picture perspective of our Earth as a system. And these sensors operate in different parts of the electromagnetic spectrum, depending on what they're observing. So some observe in the visible range, what you see on Google Earth, for example, those are visible images. The problem with those is that whenever there's cloud cover, you cannot observe those areas. And this is a huge limitation in areas like the tropics, where there is constant cloud cover, or in the extreme latitudes, north and south latitudes, where there's darkness for a large portion of the year, right? So there are other sensors as well. I specialize in the use of radar remote sensing. So that's a system where we send a signal. So we have our own illumination source. We send a signal, and that signal, when it reaches the surface of the Earth, it will scatter in different directions, and part of it scatters toward the satellite. And so through some complex processing, then we have these what's called radar images. And the advantage is that because we have our own illumination source, we can penetrate through clouds and we can observe the land surface regardless whether it's day or night. Okay, and then this graph down here shows that there are windows of observation. So over some frequencies, we cannot observe the surface of the Earth because you've got the atmosphere, and that acts as a barrier to observing the surface of the Earth. So we need to observe and design these sensors around these windows, these observation windows. Okay, so I'll talk a little bit now about the type of observations that we're making related to our planet and how we monitor our planet. So, there's a greenhouse effect. It's a natural effect on our planet. If it weren't for the greenhouse effect, it would probably be an uninhabitable planet. So we wouldn't have like the average 15 degrees Celsius that we have on Earth today. It would be a much colder place to live in. So the issue with the greenhouse effect is that it's a blanket around our planet. There's these these heat trapping gases. You all know about those, CO2, methane, there are a number of them. And we are increasing the concentration of these heat trapping gases, and therefore that blanket is getting thicker and our planet is getting warmer. So one of the things that we can do from space is measure atmospheric CO2 concentrations. And this is a graph showing, it starts from 2002 on a monthly basis. Let me just explain a little bit here. The lighter colors, the lighter yellows, whitish colors are lower concentrations of atmospheric CO2. And the orange, reddish colors indicate higher concentrations of atmospheric CO2. So through this time period, you'll see a shift globally in atmospheric CO2 concentrations, from yellowish to orangish to reddish. Right, so overall, there's been an increase, and this goes through May 2022. Overall, there's been an increase in global atmospheric CO2 concentrations, and this is kind of the quantitative graph of that animation that you saw. So there are two things here. I'll explain this variability in a little bit, but overall, there is a constant increase in atmospheric CO2 concentrations. And it is consistent, that increase. Okay, and so where we are today, just to put things into historical context, we are at 423.6 parts per million. That was the average for June 2023. And if we go back in time and we look at ice cores, so ice cores have trapped air bubbles in them, and we can analyze what the composition of our atmosphere was going back thousands of years. So if we do that analysis and we look at the CO2 levels and those trapped air bubbles, we can see that really historically, if we go back 500,000 years, the atmospheric CO2 concentration levels did not go past really like 280 parts per million. So it wasn't really until the beginning of the Industrial Revolution that we started seeing a sharp increase, sharp and constant increase in atmospheric CO2 concentrations. So these are really unprecedented times for us as humans. So as that blanket gets thicker, obviously, there's more heat that's trapped, and the temperature is increasing globally. So what you're seeing here is global temperature anomaly. And obviously back in the 1880s, these are like 5-year averages. Back from the beginning of this, we didn't have satellites, but these are models that are used. There were some stations, some measurements at that time, plus models. And more recently, with the satellite era, we incorporate satellite measurements into these type of products. So the bluish colors indicate that it's cooler than normal. The yellowish and reddish indicate that it's warmer than normal, right? So as this animation moves forward in time, we see, oops, I'm not sure what happened there. We can see a shift in the colors overall globally from bluish to yellowish to reddish. Okay, so overall we're seeing an increase, a shift in temperatures where our planet is warmer than normal, and that normal in this case is compared with the average values between 1951 and 1980. One thing to note is that these temperatures, we talk about Earth getting warmer, and we talk a lot about 1.5 degrees Celsius, which is kind of an important threshold that we don't want to pass. But there's global mean, and then there's what's happening in your local area. If you look at this graph, you'll notice something interesting, is that it's much warmer up here in the northern high latitudes and in Western Antarctica than the rest of the planet. So really, the northern high latitudes are ground zero for global warming. This is where the majority that impact is occurring. I mean, the rest of the planet is seeing the impacts, but the northern high latitudes is really seeing those impacts. So here's how that looks. And most of that warming has occurred since about 1980, around here. So we're about 1 degree Celsius overall above the normal, the average. So one thing I wanted to show that I think is really cool, I talked about the northern high latitudes, and I showed you this graph of atmospheric CO2 concentrations, and you see the seasonality. So that seasonality, that's the vegetation in the northern high latitudes during the growing season, during the spring. It's taking up CO2 from the atmosphere. And during that period of time, atmospheric CO2 concentrations drop. So then you've got the fall and the winter, and there's millions of hectares of vegetation. So during that period of time, the vegetation then goes into a dormant state. There is minimal exchange of gases between the atmosphere and the vegetation. And so then those atmospheric CO2 levels kind of rise up again. And so you see that yearly cycle, right? That uptake, and then the CO2 concentrations go back up. And this is really important because the vegetation in the northern high latitudes play a super important role in atmospheric CO2 uptake, right? And these are large areas. These are millions and millions of hectares in Alaska, Canada, Eurasia. And so what's happening in these areas is that with increasing temperature, right, you have less snow cover or less snow. And this has an impact on that ability of vegetation to take up CO2 during the growing season. So there are two things that I want to, before I go into that, this shows what I'm talking about. So this is carbon dioxide. So the yellowish colors are carbon dioxide. And the greenish is vegetation productivity, vegetation greenness. So you see when the northern high latitudes green up, there's a reduction in atmospheric carbon dioxide. So theoretically, you would think this is a good thing, right? Because the warmer these areas are, the longer the vegetation growing season in the northern high latitudes, the more time the vegetation has to take up CO2, right? So the more CO2 it's going to take up, in theory. However, that's not quite the case because vegetation in these areas have less water availability. As I said, the snowpack is less, so you've got a lot of snow melt in spring, and then by the end of summer, there's less water, for trees to draw on because the snowpack was thinner, right? So they become water stressed, or they also become heat stressed, the trees. There are a lot of more days now in these areas with extreme temperatures where the vegetation gets hit with like extreme temperatures, 90 degrees, but this vegetation is cold weather adapted. So you hit it with a couple of days of like 90 and 100 degrees, and it becomes heat stressed, and it stops that exchange of gases between the vegetation and the atmosphere. So one thing is what happens, what you think theoretically occur, right? This longer growing season, it's better, more time for trees to take up CO2, but what's actually happening on the surface. And so one of the things I do is I do a lot of field work, and I go up to Alaska. There are sensors there to understand and to measure the amount of snow, the moisture in the soil, and how the vegetation is, what's the impact of this on the vegetation. So I just wanted to share this is part of my work as a scientist, right? It's not just sitting in an office, but I also get to go out to the field. And I wanted to share with you some of these images and videos of me in the field in Alaska, servicing one of our stations there where we're measuring the amount of snow. And this is in December in the North Slope of Alaska. And this is actually in the spring in the North Slope of Alaska. When that snow melts, there are a lot of ponds and water bodies on the surface. So looking at how that water varies from season to season and year to year. And so a lot of instruments in the field to measure that kind of stuff. So we're seeing less water availability, but also another thing that we're seeing in these areas is that the permafrost is melting. And this is a huge thing, because permafrost are these permanently frozen soils in the northern high latitudes. And these soils have a very large organic layer. So basically, it's organic material that hasn't had the opportunity to really decompose, and it's been accumulating for hundreds, thousands of years. And this organic layer can be just a couple of centimeters thick to a couple of meters thick. And it's believed that the organic layer in these areas contains about 2.5 times as much carbon as the entire atmosphere. So the concern is, with increasing temperature, you've got this permafrost that is thawing and releasing that carbon that's stored in them as either methane or as CO2 into the atmosphere. So it's very concerning. There are studies. It's difficult to study the permafrost with satellite data, because satellite the measurements normally do not penetrate into the soil. So it's really difficult to understand that variability and that loss in permafrost. Sometimes through subsidence of the soil, you can then have an idea of the amount of permafrost that is being lost. Or sometimes you flat out see it with like trees just being kind of knocked over. They're called drunken trees because they're kind of leaning sideways. So there are indicators of melting or thawing permafrost, but it's not always the same indicator, and it's not always that easy to detect, especially with satellite data. So keeping our focus in the northern high latitudes and the impact of this increasing temperature on ecosystems, there's obviously as well the loss of ice, right? And loss of ice in these areas, it occurs in two ways: loss of ice on the water and the loss of ice on land. So here we're looking at loss of ice on the water. This is the Arctic, and this is the Arctic sea ice minimum area. So this is measured with satellites. Actually, we have a long continuous record of Arctic sea ice since 1979. So that minimum is measured around, it occurs usually around September, right? And this gives you an idea of that variability, that minimum from year to year. And so overall, we're seeing a loss of about 12% of ice per decade in the Arctic. And what are the implications of this loss of ice? Because it is floating ice, is that when you remove that white surface, then you expose the dark water, the dark surface. And what happens is that that dark surface will absorb the sun's energy, right? As opposed to the white surface, which reflects it. So that causes the water to warm, and that leads to it kind of it's a positive feedback. So that causes more warming in this area, right? Or accelerated warming. So the other ice that is melting in these areas in the extreme latitudes is ice on land. And this ice on land is quite significant. When this ice on land melts, it ends up somewhere. This water ends up somewhere, and that's in the ocean. So that is in part what causes the oceans to rise, right? That ice on land, when it melts, it ends up in the oceans. The giants of ice, of this stored ice, are Antarctica and Greenland. So for example, Greenland has these ice caps that are kilometers high. And if you were to melt all of the ice on Greenland, the oceans would rise about 7 meters. That's not going to happen, but that just gives you an idea of the amount of ice that is stored just on Greenland. And one of the things we can do with satellite data is measure the amount of ice that is lost in these two giants. And that is using a satellite called GRACE. And GRACE, I showed you the electromagnetic spectrum and how these satellites have operate in different parts of the spectrum depending on what they're measuring. GRACE is special. It doesn't operate on any part of the electromagnetic spectrum. What GRACE is doing is it's measuring the gravity pull of our planet. So there are two satellites, and these satellites are trailing each other, right? And so the one that is behind is measuring the change in distance to the one that is in front, right? So whenever there is a large mass, say Mount Everest, the gravitational pull is going to be a little larger, right? So that satellite in the front is going to be pulled in and the distance is going to change. And so if the mass, and this happens in areas where, yeah, and sorry, after it goes over Mount Everest, then it won't be subject to that gravitational pull, so it'll come back up a little bit, right? So that distance will normalize. So if the mass around our planet is always the same, you'll see those same pulls, that same change in distance whenever you go over these areas of larger mass, and then of less mass, you know, it'll normalize. However, when there is a change, then there is going to be a difference in those, in that scale. It's like stepping on a scale, right? So it's really cool how GRACE makes these measurements of mass loss, because large changes in mass are caused by changes in water, right? So these areas are losing so much water that that gravitational pull is different from month to month even. And these satellites are measuring that change in gravitational pull and translating that to the amount of water that is lost in these areas. And so what you're seeing here in this animation is the amount of mass change in gigatons in Greenland and in Antarctica. So there's a larger overall mass change in Greenland as there is in Antarctica. Antarctica, we're seeing a large amount of ice loss in especially Western Antarctica. In Greenland, it's pretty much kind of all around its coastal areas. But we're talking about gigatons of water a year. And so I made a calculation so that you can kind of visualize how much water that is. So what would be the amount of ice loss in Greenland? What would that equivalent be? And it would be 69 million size Olympic pools of water each year. So that is a lot of water that is melting and being released to the ocean. So another thing that we can do with satellite data is measure the sea level change, those variations in sea level. Again, we always talk about, and you always hear like these global averages, but sea level is one of those things. Sea level change or variations is very regional. It's going to depend on many things. It's going to depend on the bathymetry, on the currents, on the temperature and winds and vapor pressure deficit and the salinity. So it depends on many things. And as you can see in this image, the red areas are areas where there's been a higher level of change and or above normal, sorry, let me go back. And so there is a greater change in or increase in sea level in certain areas of the world as opposed to other areas. And sea level rise is driven by two things. So we talked about melting ice on land, that water ends up in the ocean, but also by the thermal expansion of water. So when water heats up, it expands. It's very little, but if you take up, the entirety of the ocean, which is 2/3 of our planet, it makes an impact, right? So those are the two main reasons that we're seeing sea level rise. Okay, the thermal expansion of water and the melting of ice on land. And overall, the oceans are rising at about 3.4 millimeters per year. But as you saw, that varies from area to area. So another thing that we can see through satellites in terms of monitoring how our planet is changing are fires.
This colorful view from the NASA climate model.
And fires, we can detect these using thermal sensors. So these sensors, and you've probably all seen those cameras, those thermal cameras, they point at you and like your hands might be really cold or really warm, or your nose. So the same thing with our planet. We're pointing these thermal cameras and we can detect hotspots and identify those hotspots as fires. So we use this thermal data to identify the frequency of fires over our entire planet, the extent of fires, and how these are changing from year to year. And obviously, and it's been a lot more in the news that not only the incidence of fires has been increasing, but the extent and the intensity of fires overall has been increasing. And this year has been a particularly terrible year in terms of fires in Canada already, and we're still early in the season. So I mentioned earlier, like international collaboration and satellite data and what happens in one part of the world affects others. So this shows you the dispersion of aerosols across our planet. And so we have different things here that are being shown in this video. One of them is carbon, sulfate, dust, sea salt, and nitrates. So let's just focus on the red. These are emissions from fires. And you can see how these are being just distributed across our planet. And by the way, this is like the Sahara dust right now in the news, where there's news about the plume of dust from the Sahara reaching southern Florida. And this is normal. These are normal patterns. This has occurred for centuries. We have records of this occurring. In fact, it's believed that the phosphate from this dust has helped fertilize the Amazon. But that's another story. Let's just focus on the carbon here that are emitted from the fires here in the Amazon, here in Africa, and then we'll see some really big events of these fires occurring in Australia further on here, and how that impacts the air quality in other parts of the world. I'm just gonna. So there you had these big events in Australia in 2019, these huge fires. So these are there. Yeah, and this is stuff that's distributed around our planet. In fact, another component that impacts the changes that we're seeing in ecosystems is a soot, what's called black carbon, that's emitted from these fires. And that stuff is deposited on snow. So you have snow with a black surface, which then melts quicker, right? So there are all sorts of implications, but with data, with satellite data and models, we can understand, or better understand how these things are distributed and what is the impact of these events in different parts of the planet. Okay, so to close, I wanted to show you like how change in policy can have an impact on our planet. And this is an example of the Montreal Protocol. So you've all heard of the ozone layer. There are chlorofluorocarbons that were destroying the ozone. The ozone protects us from skin cancer, and it protects us and animals and plant life from being charred. And so there was a big problem with the ozone. It was disappearing, and scientists discovered that the reason was because there were these chemicals that were destroying the ozone. So back in 1987, a protocol was signed to ban the use of these chemicals. And so since then, the ozone has started to stabilize, and eventually it will recover. But what this shows you is the ozone concentration. So very blue means that you have a very thin ozone, and yellowish and red means you have a healthy, thick, bluish, cyan, yellowish, red. You have a healthy, thick ozone that protects us. So what this shows is this is our planet projected onto 2065 with the Montreal Protocol, which banned the chemicals that destroy the ozone. And this is our planet projected to 2065 if that protocol would have never been implemented, right? So it would be a very different planet, and it would probably be dangerous to walk outside if that protocol would have never been implemented. But that just shows you how science can drive policy and how these policies can make a change. Okay, so I've just given you a very brief overview of how we study our planet using satellite data. You can find a lot more information online. I suggest you visit the climate.nasa.gov website. There are also other websites where you can access satellite data. I'm happy to have conversations with you about data that you might be interested in pulling into your projects, and I can advise you on which type of data and where to get it. So with that, I am now open to your questions. Thank you very much for your attention. And I see there's been some things in the, some comments in the chat. Let me see if there are any questions. No questions, but anyone have questions here?
What specific data do you use, and like what projects maybe kind of are you trying to work on right now or like before?
Yeah, so I showed you many different types of data. I specifically focus on terrestrial ecosystems. So looking at the vegetation growing season length in the northern high latitudes that I showed you. So I use radar imagery to look at the start of the growing season and the end of the growing season and how that is changing from year to year. And what are the implications of that in terms of carbon uptake? I also use radar to look at wetlands. So radar, as I mentioned, it has its own illumination source, it penetrates through clouds, but it also penetrates through vegetation and is a super great sensor to indicate whether there is standing water above vegetation, so whether vegetation is inundated. And the reason this is important is because wetlands, they tend to generate methane. They're huge carbon sinks, but they also emit methane. And so there's a fine balance there in their hydrology. If they're not inundated, if they dry up, that carbon that is stored in their soils can be released to the atmosphere. Right. So I use radar to study wetland ecosystems and determine how long, what is the extent of inundation and how long they're inundated, and what are the implications of that in terms of methane production or carbon release.
How many years have you worked for, like, I guess JPL or like the program in NASA kind of?
I've been there since 2009. So I started, as I mentioned, I started as a master's doing my thesis research, then I did my PhD thesis research, then I did a postdoc, and then I got hired on. So I can't overemphasize the importance of these opportunities, and internship opportunities are super important. And they might be good, they might be valuable for you in terms of opening up opportunities within that organization for you to work in the future. Or they're also valuable for you to determine what you like and what you don't like, right? It might be that you find out that what you thought was interesting to you based on that internship, it might not be so interesting. Maybe you discovered other areas that might be of greater interest to you. So that sort of exposure is extremely valuable. But what is most important, whether it's interesting or not, you should always take these things, these opportunities, and give it your best effort. Because at the end of the day, you will need references from your mentors, okay? And that will help you in the next opportunity. So you really, whatever you do, always give it your best effort, show interest, and just don't take it as a 9-to-5 job. Go beyond what is required, and that will greatly impress your mentors and your advisors. And trust me, they will note that, and that will be reflected in your evaluation or in your reference letter, or they'll even want you to come back.
Are there any like suggestions for like any schools maybe that are like good for this, like aerospace kind of major or kind of research major?
There's an internship program. So JPL, go to JPL, do a search on JPL internships, and it's open to different schools. So it's more based on your interests and your background and what sort of projects are available. One thing also to emphasize is that students wanting to do internships at JPL, I see a lot of times that they might be in good programs, or they might all have the same general coursework. You need to do something that makes you different, right? To have additional skills. And that could be hobbies, that could be volunteering work, or that could be other internships, right? But that sort of stuff helps you stand out from other students.
Are there like any colleges maybe that you suggest to go to, like as like a high school student later on, to help maybe?
It depends on what you want to study. My suggestion is try to get into the best university that you can, and one that fits your needs too, right? Some students might thrive better in a smaller university campus. Others might thrive better in a larger university campus. So that's all going to depend on you.
I think some people have like a raised hands for question.
Hey, thank you, Jeff. I think Jaden is next.
All right. I'm gonna say like that last part when you were answering his questions, you were like read my mind as far as like just a lot of stuff, because when you're explaining like that to stand out, you need to do like the hobbies, internships, and then when you do these things, create more opportunity and like stuff like that. You kind of read my mind because that's what I was thinking of to ask my question, and you answered like some parts of it, right? And then you explain, geez, man, you just, I don't know how to explain it. You read my mind, but I'm just gonna go ahead and like ask the question. But like, what kind of skill sets and like personal traits does JPL really look for in a person? Because you can just be like any other person they hire, and it's like, okay, we just have another scientist. But how do you like? How are you able to be that person who's like, that's more than the scientist? That's someone who's engaged with their work. They're very passionate, and kind of. And one person that comes to mind is Peter. Like that's pretty much who I think of like for this. So how would I be the Peter of JPL?
Well, Peter has hold on. So Peter certainly has a lot of enthusiasm. I think you cannot take away enthusiasm, right? That totally, and I'll tell you, with my experience working with different students, I could have the brightest students from the best universities around. If they come in unmotivated and just take this as just a job, 9 to 5, they go home, they're not really engaged, I'm not really gonna seek to have them back, right? But someone that comes in enthusiastic, willing to learn, that is resourceful, that's important too. I remember mentors tend to be very busy. We don't want you to spin wheels, but it's difficult to be bombarded with questions throughout the day. So people that are resourceful is important. And just showing that, yeah, you're really trying. There is a lot that goes with people trying and trying to understand and trying to figure things out.
Thanks, Erika. And I also would just like to say here is that, we've been trying to provide that sort of comprehensive preparedness by the having your peer mentors work with you on the science teamwork and leadership piece, because really those kinds of skills that support you in having the interactions that are really, really positive when you're working with mentors or when you're working with your peers. Those are the kinds of things that also really catches the mind's eye of people that are making decisions. So I just want to give us a plug here, Erika, for all the work they've been doing with the teamwork. And we do ethos of science, we do intellectual humility, we talk about diversity, like all these different things that are really critically important, and that NASA is looking for when they're looking for employees. So I just wanted to build on that, because enthusiasm can get you so far, but you also have to have those other things, of which Peter already has the whole package. So yeah. So let's go to Grace. Jaden, if you have another question, we can come back to you. We still have a few minutes.
Okay. Hi, Erika. So I also, you answered a few of my questions, and I definitely have like a better understanding of certain things. But I did want to touch back on something you were mentioning earlier. So when you said like different coursework to stand out, like what exactly would you suggest? Like, would it be along the lines of like Mae Jemison, who did stuff like dancing as part of her college career, or something more along the lines of like exobiology, which if you're like going into aerospace engineering is still sort of space related?
Yeah, I think that's a great question. I would say things that help you build your professional skills. Because I have gotten resumes too, where people say, well, they can lift whatever, 100 pounds or something like that. And that's good. It might be a good skill for something, but not for like remote sensing, image analysis, or a science project necessarily. So I would suggest like joining clubs too, interest clubs through your high school or through your university. Sometimes hobbies like making things, coding is so important. Whatever you do, you guys have to learn how to code. Nowadays, if you're going to do analysis, you can't do analysis just based on what's out there, the tools that are out there. You need to develop your own tools. So coding is super important. Like building things, Arduinos, using Arduinos, being part of the GLOBE program and making measurements of environmental variables, things like that, that give you an edge into your professional. Yeah, obviously personal things are good too. It shows that you have diversity. You know, if you're like chess champion or dancing ballet, I mean, that's nice to have. I'm not saying don't do it, but yeah, what kind of stands out from the professional part is really what sort of skills can you bring that can help in the project.
Excellent. Thank you.
Could I just touch back and ask one more thing real quick? I promise you it's really
Sure, go ahead.
Sure.
Do you have any internships, high school or undergrad, that you'd suggest for anyone hoping to go into like aerospace sort of things?
Yeah, so there are internships. There is a high school internship program. You guys are in starting your senior year, right?
I'm going into my junior year.
Junior and senior.
Okay, so there is it's called a spaceship program at JPL. It's not on every year. I don't know about other NASA centers. You would have to look. They are quite limited, unfortunately.
Great.
But there are.
Also, yeah, and also, you know, I mean, the NASA ecosystem is a really exciting place to look, but there are also lots of wonderful opportunities that are offered through universities. I'm here at the, at the University Corporation for Atmospheric Research. They have incredible internship opportunities for students once they are undergraduates. So, I think that internships are limited everywhere you go. But if you keep looking, I think it's pretty likely that you will find a good fit for yourself. So thanks for those questions. We have a couple more minutes. Daphne.
Oh, hi. I wanted to know if there's like somewhere I can find data for wind, like the satellite data you showed us, but for wind.
Yes, so I think GLDAS. Yeah, look there, GLDAS. I think they have a wind data. Feel free to send me an email and I can send you more information.
Great, thank you.
Thank you.
Great, we have one last hand up, and that's Ria.
Hi, Erika. I really loved your presentation. It was so informative. And I was particularly curious about a little bit about what really draws you to earth science research and what sort of skills you think help you succeed there. Because I'm thinking about research versus industry, although I definitely want to go into earth science. And I'm just wondering about what made you choose research.
Yeah, that's a great question. I think it was just my path. I can't really compare to industry because I've never been there. This has been my only job, but I think it fit my overall vision about wanting to have a positive impact somehow, and that would be by better understanding our planet, and hopefully that sort of information can help people understand and change. So that's really my motivating factor.
I love that. It's sort of it's a little bit altruistic, isn't it? And I appreciate that too. We need those visionaries and those people that have some inherent altruism to want to make the world a better place and to help humanity and all of biodiversity and everything. And Jaden has his hand up again. I said I thought we might be able to circle back to you, Jaden. I think we can. I think she can take one more question. Go ahead.
All right, thank you. So I know everyone wants to ask about internships and opportunities for the future. but I'm also curious about current opportunities as far as shadowing. Like, if you do online work, is there any way I can like kind of have a like inside like sneak peek of it? Like, show me the processes of what you do. Show me a good day, a bad day, all the work that you would normally see during your job. And if I'm not able to job shadow you or just see some of the things that you would do normally, do you think that there's anyone else that you could like help me network with?
Yeah, I understand. I mean, I think that's a great idea. I don't know of any programs that are in place for that. As a scientist, it's kind of tough. Our days are very different. Every day is different. Meetings, conferences, field work, there's all sorts of stuff. So I think it's a great idea. I can float that up to see if there might be something like that already in place, or maybe if they would consider doing something like that.
Yeah, that is a really great question, Jaden. And I know that job shadowing is something you see a lot in industry and in business, but I have never heard of an experience like that with science. It's almost always, working with a mentor and helping them with projects. And I just also wanted to mention that, there is a program through the National Science Foundation that every year they have really thousands of positions that are available for students that are interested in working in a scientist's lab. And you can look and see what those opportunities are. They're all posted. It's a really another great place to go. In high school, it's pretty tough. There are relatively very few things that are out there. And that's why Peter and I and Cassie were really committed to doing this program with you guys. Because I think it is really important to get a taste of what you like and what you don't like, early on in your emerging career. So, I think it's really interesting. It might be, I was just thinking it might be fun to do something to create a program, Erika, where we could do a day of job shadowing as something that NASA could do as a kind of a way to engage. NASA's always wanting to engage its science mission experts in connecting with the public, and maybe doing a shadowing experience might be one of those ways that could potentially be very, very powerful. So I want to thank you for that question, and I want to move on to Semarin.
Yeah, I just want to say thank you, Dr. Podest. But one of the things I wanted to ask was, I remember you mentioned that you got an electrical engineering degree. So I wanted to ask, how was your experience with that? Because that's something I'm interested in pursuing in university. And I was wondering how you thought it kind of affected your career choices, later on.
That's a super great question. I'm glad you brought that up, because I went into electrical engineering not really knowing that much about it, knowing it was a tough one, and also with the altruistic view that with technology will make the world a better place. Honestly, as I went further into my courses, the deep electrical engineering courses in the third year and fourth year, I realized that it was probably not the field I wanted to pursue. I just found it a little dry, and I didn't really saw how I could connect it with the environment at that point in my life, until I discovered remote sensing, right? Which remote sensing, I mean, you can develop a satellite, right? And you need an electrical engineer. So there are all these things that there's medical stuff where you need an electrical engineer. So, however, going into remote sensing, I am an engineer in my bachelor's, but I'm a scientist now. And it gave me a huge lead to go from being an engineer into a scientist, because I had the technical background to be able to not only do science, but do science in a very rigorous way, where it's very important to understand some of the physics, to understand the signal interaction with the land surface, to do modeling. So I think it's easier to do that, to have like an engineering background, and then you can really choose what you want to do, as opposed to having maybe a softer background and trying to go into engineering or some of the hard sciences.
Great. Thank you so
Okay,
much.
thank you.
We have been, it's been over an hour, and I just want to, I would like to thank Erika for all of her contributions to this discussion, and also thanking you for some really fantastic questions. And I think you can see why Erika rises to the top as one of the scientists that I really would, I really look at as a role model and someone that I would like to emulate in my career. So Erika, you've just always been so amazing. And the last thing I wanted to mention was, you did talk about, your early experience and how you really became really aware of nature, through working with your dad and your brothers and going out in boats and things like that. And those are really also really important things that you may not consider would have a strong, what do I want to say? Have a strong
relevance, maybe, or
thank you. I'm not feeling well today, so my brain is like not working. But yeah, you may not think that might have relevance. And I just wanted to say, when my husband was looking, he eventually was running a lab at University of Minnesota. And besides saying we're looking for a PhD with this much experience working in this area, the ideal candidate will also have experience with boats and have a sailing license and know how to do knots and all these weird things. And it was like, that job was perfect for him. He was like the top candidate because of a hobby that he had developed, when we were living in Germany. So, I think part of what that Erika's life really tells us about is you can also sort of follow your passions organically, and don't stop doing something because it doesn't seem to fit in what you think you're going to be doing, because we'd have no idea what those jobs are going to be like in the future. But all these experiences that you do have really great relevance. And can you take one more question?
Yeah, absolutely. Go ahead.
I don't know what your schedule's like, but Shreya has been sitting here patiently with her hand up, and I would like to call on her and let her have the last question this afternoon.
Oh, sorry, I did not have my hand up.
Oh, you did not? Okay, then. Well, then I think that that concludes the session. I put Erika's email in the chat. You can also find it on the on our Mighty Networks. But Dr. Podest, you said that you are welcome. You will be happy to welcome any questions or comments, and you're going to give someone some more information on GLDAS data. And also, I think that a lot of your projects would really benefit from talking to Erika, either maybe next week, if you want to make an office hour with her. She has a lot of insight about the projects that you are doing. All of them connect to climate change, right? So that's, I think, the last thing I'm going to say. And so thanks, Erika. Thank you for coming, and we look forward to working with you in the next week.
Thank you very much, Rusty, and thanks to all of the participants. You guys had great questions, and I look forward to interacting with all of you, hopefully, during the next couple of weeks.
Great, thank you.